Hi, everyone, and welcome to the latest in Beaconr's webinar series. My name is Mark Higgins. I'm the Chief Analytics Officer here and co-founder at Beacon. Today, we're going to look at a pretty common use case at banks, how to implement a new type of financial instrument. In this case, a kind of structured note called a barrier reverse convertible note. We'll get into what that means in a minute, but let's start with what we need to do. So first, we need a way of representing the contract terms of the trade, the stuff that shows up in a confirmation agreement. Beacon has a hierarchy of Python classes that represent different types of financial instrument, and we'll extend that to add this new instrument. That instrument needs to know how to price itself. So we'll incorporate a couple of pricing models. One will be the default pricing model, and the other will be a comparison model. It also needs to know how to evolve itself through life cycle events. So these are things like coupon payments, option exercises, knock-ins, and that sort of thing. We'll walk through how to support that kind of event in Beacon instruments. It needs to be properly tested. We're building real production code here, not just R&D stuff. So we'll take a look at how Beacon's test framework works and walk through how to do a historical hedging simulation to make sure that the model is giving sensible risk numbers. We'll talk about how to integrate model risk management into the workflow, since that's an important part of deploying new instruments today. Business people, so that's structurers, traders, salespeople, portfolio managers, they need to be able to price this thing. So we'll walk through how to expose your new instrument in Beacon applications with a focus on our Beacon Quote pre-trade structuring tool. And the last, most important step, deploying your changes into the production environment so that the business can use it quickly. This is one area where Beacon really shines. Developers using Beacon can build new functionality and deploy it into production quickly at the speed of a trading business, while still satisfying all the complex control requirements that a modern business needs to support. So the instrument we're going to build today is called the Barrier Reverse Convertible Note. It's a flavor of equity structured note. Basically, it is a kind of fixed rate bond. It has a fixed coupon. So there's a bunch of fixed rate coupons and then principal repayment. And typically, you get higher coupons in these kinds of bonds, these barrier reverse convertible notes, than you get in a regular fixed rate bond because the buyer is selling volatility. Basically, it looks kind of like a regular fixed rate bond less a down and in knock-in put option. So in this example here, on the x-axis is the underlying asset price, like the stock price, and on the y-axis is the P&L. So in this example, the strike price of the put option is 100, and the barrier price is 50. So if at any point during the life of the note, the stock price ever trades down through $50, then this put option gets knocked in. And what that means is the coupons are still paid off the full principal, but the principal repayment at the end gets discounted if the stock price ends up below the strike price of the option. So instead of getting your full principal back, you might get some discounted amount, right? So in return for potentially getting less of your principal back at the end than normal, the coupons can be higher. So that's the barrier reverse convertible note, and that's what we're going to be implementing today. One of the unique things about Beacon as a trading and risk system is that we give our clients a full set of enterprise development tools as well. So not just a collection of APIs, which you always run into the edge of. What that means is clients can use the same developer tools that we at Beacon use, and they can build their own extensions to our tools or build even their own new tools in general. One little side note, for real structure, one of the important pieces of market data for structured note stuff is the funding spread that you apply on top of regular discount rates when you're discounting future cash flows in these structured note payoffs. If we're doing this for real, we connect that into market data for credit data and funding spreads. We already have in Beacon an existing structured notes framework to do that. We're not going to use that here just to keep things simple. We're going to build it standalone where you just manually specify the funding spread. All right, so before we jump into the weeds and take a look at the code, just wanted to give a high-level view on what we're trying to do. Instruments in Beacon need to define three main things. So the first one is contract terms. next is pricing, and the last is lifecycle management. Contract terms correspond to the stuff that you put into a confirmation agreement, but only for one unit notional of the instrument. Deals in Beacon basically say, I want to buy some notional of some particular kind of instrument, so the instrument itself is unit notional. We use an object-oriented framework to describe the instrument, which is pretty normal. One thing that's interesting about Beacon is that we also use an object-oriented database to save the data about the instrument rather than a relational database structure. We'll talk a little bit more about that later. For pricing, so if I have an object that represents this barrier reverse convertible note financial instrument, when you ask for a price on it, that price gets delegated on the fly to a pricer object, and that the type of pricer object is specific to which kind of pricing model you're using. When we give our clients all the reference instruments that we've built in Beacon, they all know how to price themselves using Beacon's own quant libraries, our own reference analytics. But a lot of our clients have their own quant libraries that they want to use instead. And so we've designed this whole pricing machinery to make it easier for clients to build their own pricers that wrap up their own quant libraries. One interesting thing about Beacon instruments that isn't true for all systems is that Beacon instruments know how to life cycle themselves as well. So by life cycle, what I mean are the events that happen to derivatives and securities through their lives, like option exercises on the exercise date. If it's in the money, it exercises into whatever the underlying thing is. If it's out of the money, it turns into nothing. If I have a swap or a bond, there may be regular coupon payments. If it's an instrument like this one that has knockout barriers and you have to keep track of barrier breaches. So Beacon instruments know all the different kinds of events that can happen to themselves and what the positional impact of those events are. There's two main categories of event. There's schedule events. Those are things that happen on known dates like coupon payments or option exercises. And then there's unscheduled events, which are things like barrier breaches or American option exercises that happen on uncertain dates. Those are unscheduled events. And then Beacon's deal model asks the instruments, what positional effects they expect to be able to go and implement the lifecycle events. Beacon isn't just an R&D environment, it's a full trading and risk management system. And that means it's not just an R&D tool. Once you've built this instrument, you need to be able to expose it in applications that business users can use. There's pre-trade applications like in Beacon, our main pre-trade application is called Beacon Quote. That lets you set up new multi-leg deals, connect to real-time market data, run risk on new deals, things like that. There's also applications like our Trade Blotter that lets you look at existing deals, book new deals, manage lifecycle events, run risk and P&L on existing portfolios and things like that. Exposing your instruments in these applications can often, in a lot of systems, can be kind of a pain in the sense that there's going to be one team, like the quant team, that builds the representation of this new financial instrument and plugs in the pricing, and then a separate team, the technology team, that wraps that stuff in the user interface. And that works, but it's not very efficient. It'd be cool if the quants could do the whole thing themselves. Now, I'm a quant. Hopefully, I'm not going to offend any quants by saying quants typically aren't very good at user interface stuff. So we spent a lot of time building our user interface framework in Beacon so that quants can do this themselves. Basically, just say, as you define the different methods on the object that corresponds to your financial instrument, you just tag those methods that you want to see in the UI with a special tag, and that defines which fields show up, how they're formatted, and things like that. It's easy for quants to do, as we'll see, and that gets automatically picked up by the application, so a quant can do the whole thing. So let's jump into our Beacon integrated development environment, our IDE. This is where developers write code, test it, deploy it to production. Our IDE is based on Microsoft's browser-based open source Visual Studio, though it's got a bunch of custom workflows attached. Some of the cool things about this, it runs in your browser, which means there's nothing to particularly install on your computer. So, if you're doing hybrid work, sometimes in the office, sometimes at home, or if you're traveling to different offices, you don't have to have anything special installed. You can work really easily between different computers. This development environment gives you the same developer tools that our internal developers use. So we don't give you just great trading and risk tools. We give the developers what they need to be able to customize it for your own business. The code that's available in the IDE here, you can kind of see a little bit of it on the side. The code that a client's developer sees is a combination of Beacon supplied code as well as the client's own code. And they're all separated into a bunch of different Git repositories. Git is our version control system that we use. So clients can see all of our source code. It's read-only, so you can't change our Beacon-owned code in production, but you can see all the code, you can debug through it, you can use it as templates for new stuff you build, and you can use it to extend. And the way you extend it is by writing your own code that lives in your own client-owned writable Git repositories, so you can change all that code. So in this script here, I've got the code for the stuff that we're going to be looking at, and here is where I define the class for this new financial instrument. This inherits from this base class instrument, and so this base class and all the derived classes are examples of what we call grommet classes. So grommet is a really super useful framework, which is a dependency graph framework. For graph theory nerds, it's an acyclic dependency graph. For normal people who don't know what dependency graphs are, you can think of it kind of like Excel, where methods on the grommet objects are equivalent to cells in a spreadsheet that can all depend on each other. This gives you a lot of really powerful functionality. It gives you dependency tracking. So you can say, for example, if I've got a portfolio, run down through the dependency graph and figure out all, say, the stock prices that I depend on. If I want to run an equity delta report, I need to know which equity prices that I need to shock. Lets you do that easily. It gives you optimal caching. So if I've got a portfolio that has instruments that depend on 50 different prices, I can price the portfolio once, everything gets calculated. Now, if I want to bump just one equity price, leave all the other ones unchanged, and then price the portfolio again, only stuff that depends on that one equity price needs to get recalculated. All the rest of the stuff gets cached. And also, if you've used Excel, you know how useful it is for debugging to expose intermediate values in cells in the graph. So the equivalent of that is just being able to see intermediate method values in the grommet dependency graph, and it makes it a lot easier to do debugging stuff. We use grommet to optimize financial calculations like risk and scenario reporting, but we also use it in our user interface framework, our UI framework, to signal when changes are made and what other UI elements should be updated by the changes. So it's a really powerful tool. So this is just a regular Python class. So I've defined, say, this method ticker here, which defines, which equity index we're pointing at. Any method that gets tagged with this @grommet.fn decorator means this method on this Python class gets mapped to a node in the grommet dependency graph. So not all methods on your objects have to be ones that are tied to the graph, but if you want them to, you just tag it with grommet.fn. Now, some of them you'll see, have this grommet.stored flag, and some of them don't. The ones that do are stored values. These are things that are saved to the database. So these are like the contract terms of the instrument. So the ticker, the strike price of that knock input, the barrier price, the tenor of the bond, all that kind of stuff. So these are contract terms. They're tagged as stored. Again, just wanted to highlight that the main data store in Beacon isn't a relational data store, but this object store, which is built on top of MongoDB. Beacon also supports relational databases because there's lots of data where a relational database is the right tool to use. But in general, for financial instruments, for financial data, there's a lot of different shapes of data, and those shapes can change sometimes, not all that infrequently. And managing that kind of complexity with a relational database can be quite difficult. Using an object database makes it a lot easier. We also have values that can be overridden. So here, for example, here's our funding spread. Again, if we were doing this for real, this would be connected into market data. But for this example, we're keeping it simple. And this is something that we can override. So this basically, if a thing is tagged as can override, it means I can put a temporary value on it that it'll just remember, and then I can erase it later and I'll have to go back to the default. This class inherits from this other base class called instrument pricer mixin, which defines the framework for delegating pricing to pricer objects. So the main method that gets defined in here is premium price. So premium price is the name of the method that represents like the price of the thing. It corresponds to the price of one unit of the instrument in its denominated currency for value date equal to the standard premium exchange date. So when premium price is called on the instrument, it gets on the fly. It says, I'm going to build a pricer class. I'm going to build an object of an appropriate pricer class, and that pricer class is defined through a method called pricer type, and the default for that is default pricer type, which is just the string name of a class. Here I've got it hard-coded. For production stuff, this ends up coming from a time series. So you have a piece of reference data which corresponds to the current pricing model that you want to use by default. This means that, you know, if you've got a particular kind of financial instrument and you want to upgrade the pricing because you've come up with some new pricing routine, on the day where you want to make the change, you just update that piece of reference data to point to a new class name, and then when you price new trades or price your portfolio or run risk or whatever, they'll use the new pricing method. But you want to be able to reproduce past data as well. So because the pricer type is typically a piece of time series, then you can go back and roll back before you made the change and reproduce the old behavior as well. This is also where you go and define your own pricing classes. So if you wanted to write your own code that wraps up your own pricing library, you'd write a pricer class and then point this guy at your new class. All right, so and we'll walk through the details of the pricing models and the pricer classes in a minute. So we've seen how you represent contract terms with these stored grommet values, and we've seen how you implement pricing at least at a high level through through delegating to pricer objects. The third thing that Beacon instruments need to do is evolve themselves through lifecycle events. And again, there's two categories of lifecycle event: scheduled lifecycle events that we know happen on a particular date, but we might not know what happens on that date because it might be market dependent, like an option exercise. And then unscheduled events, which are things that happen on an uncertain date, like a barrier breach. So here I've got some methods that define scheduled events, things like the type of the next scheduled lifecycle event, the date that it's supposed to happen on, and then incremental positions, which is like the position effects of this exercise. So for example, it starts off by saying the position effects are trade out of myself, and then it'll trade into a coupon payment. If I'm on the final date, it'll trade into the principal repayment as well. And then if the knock-in put option has been knocked in and the option's in the money, then it also discounts the principal repayment by that option payoff. There's also unscheduled events. So here's an unscheduled event for a barrier breach where, if the barrier gets breached on the instrument that hasn't been already knocked, then it trades out of itself and it trades into a new version of itself where the barrier has been breached, and adds that in. All right, so let's skip ahead now and look at the how we define these pricer objects. We're going to define two different pricing models for this instrument. One of them is using a local vol stochastic volatility mixture model. That's one of our in-house quant library things called LV state. That's going to use backward induction. And then we have a second one, which is pricing using a Hessian stochastic volatility model using Monte Carlo. Well, we'll start off with a base class for both those pricer classes. The main thing it implements is parent, which is just a reference back to the instrument, so it knows how to get the contract terms and stuff. The main method that pricers need to implement is premium price. Here I'm splitting that into two pieces, a model dependent bit, premium price zero coupon, which includes the knock-in put option, and then the price of the coupons. Remember, the coupon payments for this instrument are always paid on the full principal, not the discounted principal. So those aren't model dependent. So in this base class, it defines the non-model dependent price of the coupons. And then in the derived classes, it'll do the kind of zero coupon that includes the knock-in put. So here's the class that uses our LV state model, which is this local vol stochastic vol mixture model. And it uses backward induction to price it. So in a backward induction grid, you need some numerical parameters like the number of points in the spot direction and the time direction. Here's the method that goes and implements it. And we have some nice framework for doing this kind of stuff where if I get down to the interesting stuff, it can build this backward inductor object, which is a Python object that wraps up a C++ backward induction machine so that when the backward induction happens, it happens in C++, even though we're using Python for most of the stuff. I can add on boundary conditions like adding a knockout. I can add in the option payoff here. And then I can backward induct it just by saying go back, and then pick off the price of the instrument this way. Here's our second class that implements the Heston Monte Carlo routine. Again, it has some numerical parameters like the number of paths and time steps. And then, in the method that defines the price of the zero coupon bond, it'll go and pick off the calibrated Heston model parameters, which is already built into our equity framework. And then it builds a Monte Carlo forward inductor object here and advances it to the expiration date. And then you can go and inquire for things like what are all the different spots. These knocks are flags on, 1 if it's been knocked and 0 if it's not been knocked. And so you can go and calculate the payoff per path and calculate the average payoff that way. So once I've got my instrument defined in terms of the contract terms implemented through stored values, the pricing through these pricer objects, and the life cycle through those methods that we looked at before, now I can go and just do a little bit of play with it. So here I'm going to hit F9 and run this code. This runs this play around code. What it does is it says, switch to a particular date, just so I'm using a consistent set of data to run these tests on, construct a new instance of this instrument, and then ask it for its price. So here it prints out the first price using our default model. I haven't specified the model so far, so it uses the default, which is that local vol stochastic vol mixture model. And it works out to a price of 92 cents per dollar of notional. And then I can go, if I want, and play around with pricing models and switch it to the Heston Monte Carlo pricing and then print the price there. So here it shows a price of 94 cents. So there is some model dependence of this instrument. Okay, so now I've I kind of got it to the very beginning, the part where like I feel, when you're a developer of this thing, when you get to this point, you're like, oh, sweet, I'm pretty much done. And then you realize now I have to do testing. And that takes generally way more time than actually building it in the first place. We have a nice framework for doing testing of instruments though. So next thing we're going to do is walk through how we do that. So basically the way that instrument tests work is you generate a whole bunch of randomly sampled instances of the instrument, sort of sampling through the parameter space of the instrument, like which asset it's on, tenors, funding spreads, strikes, barrier levels, all that kind of stuff. And it generates a random instrument. And then the test, you define a bunch of different tests. So here I've got, in this super simplified example, just 3 tests. I've got one test that says when the barrier is very far away, make sure that it prices just like a regular fixed rate bond. So here it steps through all the different tests, generates a random instrument, sets the barrier far away, asks the instrument for its price, and then independently implements pricing for a fixed rate bond and compares that. Second test says, if it's already knocked in, then it should price like a fixed rate bond less a regular put option. And so here again, it runs through randomly generated instances of that and compares the instrument price against other benchmarks. Test life cycle to make sure that when a life cycle event happens, the net P&L impact of the life cycle is zero. Stuff like that. If you were writing this for real, there'd be loads more tests in here for all the different kinds of limits you tested against, different pricing methods, testing backward induction against Monte Carlo and things like that, testing for monotonicity of price versus different inputs, making sure that the price is smooth with respect to market data, things like that. But that's the framework that you do it in. And then those tests, normally this test would be in a different Python script to the one where we've defined the class. Here, this for the purpose of this webinar, I put it all on one for simplicity. But in general, this would be in a different script. And then anytime I make changes to the instrument, it'll automatically run through all these tests to make sure that I haven't broken anything by accident. Another type of test that's really useful to do is a hedging back test. Often we're required to do these kind of tests now with modern model risk governance. The idea with this is to say, if I had put on, a barrier reverse convertible note at some date in the past, and then use the model to figure out what hedges I need, what option hedges I need to hedge my Vega, what delta hedges I need to put on, and just check and see that actually putting on those hedges actually is effective. Like it reduces the variance of or standard, the sort of like day-to-day P&L standard deviation. So that's what this thing does. So this goes and says for any particular date in the past, I've got a little function here that puts on the barrier reverse callable and potentially puts on a bunch of hedges using the model to calculate the hedges. And then it can run that test. So it just like puts it on one date, holds it to the next date, and calculates 1 day's worth of P&L. One cool thing about Beacon, though, is to do this kind of testing, you don't want to just do one date. You want to run it over some big historical window and check, the P&L statistics over a long period of time, which can be pretty slow. But fortunately, Beacon has a parallel compute framework built into it called WIMP, where you can go and run all those calculations in parallel on a grid compute pool and run it really quickly. So even though this is still just testing code, I can go and access grid compute and do large-scale parallel testing. So I've run those tests here, so we don't have to sit and watch the scheduler run through tasks. But here's like the statistics for daily P&L. If I just put on a note, hold it for 1 day, this is a 1-year note. So on any day, I put on a 1-year note, hold it for 1 day, and then take it off. Let's see what the P&L is. So the average P&L, and this is on $1 million notional, so I can see the average P&L is something small and negative. Standard deviation is like $6,500 a day. If I put on delta hedges, then it reduces the standard deviation from 6,500 down to 1,200. So the delta hedging has, the model has told me good delta hedges to do. And then if I use the model to tell me Vega hedges and delta hedges, so if I delta and Vega hedge my my note, then the standard deviation drops down to $237 a day. So it's showing me that I'm doing pretty effective hedging with the model that I have. So that's a useful thing to have in there. Next thing we want to do is user interface. So I mentioned that you don't have to be a UI expert to expose things like this in applications like Beacon Quote, which is our pre-trade pricing tool. So if I go back to the definition of our convertible note class, I've got for example like which ticker it is. I've said this is a grommet function. I didn't look at this thing though. So this other decorator form field is the thing that says, if I tag this method with that form field, I want this thing to show up in user interfaces. And in this case, it's a drop-down list, and I want the choices to be returned by another grommet method called tickers. Or if I've got my strike here, this returns a float. Here's the format that I want it to format the number in. And if I'm doing solving, I can specify that as well. So I can sort of tag things to show up in user interfaces really simply in a way that me as a quant, I can do. So let's go down to the bottom of the script here, and I'm gonna just run a little test where I run our beacon quote tool. Sorry, 1 second. And in the test environment, so we can actually see how it works. So if I F9 this guy, what this is going to do is run our pre-trade application beacon quote in this test environment, where I've gone and set up this new instrument. So here's quote, here's the beacon quote. I can go and say I want to do an equity index barrier reverse convertible note in this column B. I can add different columns for all sorts of different kinds of instruments. So here it's dynamically loading up the class, and now I can go and structure one of these guys. So I can choose which ticker it is. Say I make the strike 4,000 and the barrier level 3,000 or something like that. 1 year note with quarterly coupons. Maybe I want to have a 40 basis point funding spread, so I can type that in. And right now I've got let's say I put in a coupon price of like 9% or something. That says, in that case, the unit premium on this guy is going to be $97.69 for a $100 phase. This tool lets you do lots of cool stuff, like, it shows me sort of basic risk numbers here, my delta and vega. I can do solving, so if I wanted to say, which coupon rate should I choose if I want to make the price, say, $99.50. So if I'm, selling it to a client at 100, maybe I make 50 cents profit. So this says, I'd need to have like a $10.865 coupon rate to give it this premium. So it lets me do this kind of stuff. And again, here's the fields that I tagged in the instrument to show up in here. And that's all I needed to do. I don't have to be like an expert at all the rest of this user interface to get this to work. The last thing is deployment. So in Beacon, we have a lot of useful tools for doing workflows to deploy stuff into production. Basically what you do here is you use the tools on the left to commit your changes in version control in a special side branch called a feature branch. So this is a branch in version control that can be accessed easily across the platform, but it's not yet in production. Once you create a feature branch, then Beacon will automatically run any unit and regression tests that are affected by your code change and make sure that they all pass before you're allowed to promote your change in production. Also, depending on the type of of code that you're changing, different teams might need to review it and sign off on the change and things like that. All those sign-offs are saved in the platform and then are auditable rather. And then once all those tests pass and once all the controls are satisfied, the developer can then right away promote their change in production. And this can happen as frequently as you can satisfy those controls. So it might be multiple times per day if they're light controls. And the advantage of this model means that you don't have to wait for like a bi-weekly or monthly release to get your changes into production so people can use them on the desk. It could be as soon as the same day. And that lets you develop at the speed of the business while still satisfying all the complex controls and regulatory requirements that we all know modern financial services companies are exposed to. All right, so what stuff did I leave out? The model risk process, there's a whole other side that the model risk team does in terms of independent implementation, scenario testing, back testing, and stuff like that the model risk people want to do. And that's so much easier to do when they're working in this same development environment as the front office, when they can access that code, use the same tools, write their own code using those same tools, accessing the same market data and all that kind of stuff. So I kind of left that part out, but it's really cool when you have your front office and the model risk teams all in the same environment. It's a lot easier to do stuff quickly. I also left off things like downstream system integration. So often trade details need to be sent to downstream systems for confirm generation, for accounting, for settlement, and things like that. Beacon has a nice infrastructure to manage all those conversations. Generally, it's relatively easy to design interfaces to the systems so that new trade types like this don't need a whole lot of new development work in the downstream systems. There's also external systems integration. So for like electronic market making or trade SDP or RFQs, things like that. Some structured node exchanges have interfaces for doing things like that. So this is sort of left off the work associated with doing those kind of integrations. Those are typically pretty easily extensible to new types of notes. All right, so what to take away? Beacon has this really powerful cross-asset trading and risk suite of applications and functionality out of the box, but Beacon is designed to make it easy for our clients to customize it. So quants using workflow, just like we walked through, it's easy to implement a new type of financial instrument in Beacon, really end to end. So from the kind of like R&D and pricing implementation all through exposing it in applications and deploying it out into production easily. So maybe I'll pause there and happy to take some questions. All right. Okay, first question. Do you have a scripted payoff language so that structures could create their own payoffs? So we do. We have a scripted payoff language and an instrument that wraps it up that uses that Monte Carlo framework, the same one that we use for the Heston stochastic ball model pricing in that example. But over time, what we found is that there's less need for structures to kind of script their own payoffs when a quant can do it quickly, like in this example. The reason that that's sometimes better is that when you have instruments that are defined through code, through script, it's often hard to comprehensively test the entire universe of payoffs, and it's often hard to say exactly which models are appropriate for different classes of payoff as well. When quants can go and build specific instruments for the kind of trade that structures want to do quickly, then you can have a lot more control over that kind of stuff. All right. Another question. Isn't Python a bad language to build pricing logic in because it's a slow interpreted language? That's a great question. Python's in Beacon, Python is just kind of the glue language that connects market data, contract terms, and pricers in this particular example. So like we saw with that backward induction example, when I build that little backward inductor object, that's a Python object that is a fairly thin wrapper for a C++ object where the actual calculations are done. So when it does the backward induction, it does it all in C++ in a compiled language that's nice and quick to execute. So it's the usual kind of like 80-20 rule. Like most of the code you write, it doesn't matter how fast it executes because it's not the limiting step. But a small part of it really matters. So what we think of the right thing to do is to use a really developer-friendly language like Python that, where it's quick to develop but slow to execute for the 80% of code where the speed doesn't matter. And then you use a compiled language like C++ for the fairly small part of stuff where execution speed really is critical. And Beacon makes it really easy to do that. All right, maybe one more question. Can you really deploy changes that quickly? Yes, it's often surprising to people that it's possible to do this, but my co-founder Kirat and I spent our careers before Beacon at Goldman Sachs, JP Morgan, Bank of America, where we built similar systems to Beacon. That Beacon's kind of based on those same principles, and the same control model and deployment model works with those places. So at the biggest banks that have the strictest regulatory oversight, they're able to have this model where you can really make a lot of small atomic changes rather than infrequent monolithic changes. And that helps you develop stuff at the speed of the business, iterate quickly, and all that sort of thing. All right, maybe we'll stop there. Thanks everyone. Appreciate your time. And if you have any questions, please drop us an email. We'd be happy to chat some more. Bye-bye.